Hi, we're going to follow up the rest of section 5.2. I stopped it at something called a Poisson process, and that's where I had ended the lecture on 5.2. A Poisson process, and it's actually a process, something that happens over time, and you're counting how many events happen in a certain time period. So that's why it's in the Poisson distribution section. But again, it's actually a process. You're looking on a time interval like 0 to t and counting how many times something happens on that interval. And a lot of times when I do problems, I guess I don't try to distinguish, is this a Poisson process or, yeah, I guess I just see, oh, there's a Poisson random variable involved, and I don't really use the notation the book does. So a lot of times I think in solutions you'll see that I have just represented this as a Poisson distribution where x is the number of occurrences of something over a time period. So yeah, so sorry if I don't use always this notation, but and if you go on and take other probability courses and some other math courses, you'll see different processes, and this is just, a stochastic process. So process just means something over time. So a Poisson process, you're just counting the number of events that occur over random period of time or space. So again, going back to car accidents, if you look on the interval here, like 0 to 7 days, you're just counting in that interval how many accidents happened. And maybe you're on a 7-day time frame, so the next would be 7 to 14, and then the next would be 14 to 21. So you're just counting in each of these intervals how many accidents occurred. Number of goals scored by a hockey team, a given hockey team. So if time is, let's just think continuous, we're not going to cut it at a period. So a team in the first 0 to 20 minutes, how many goals they have, or 20 to 40 minutes, how many goals, 40 to 60 minutes. And we don't even have to stop at game, we're just looking at intervals every 20 minutes, how many actual goals do they have. And again, there's a large chance for many events to occur, but if you watch most hockey, you don't see goals occurring every few seconds. There might only be one or two or none in a 20-minute time interval. Number of customers arriving at a post office. There's lots of customers going by every hour, but how many actually, go in and use that certain post office? Number of earthquakes in a 10-year period in California. Every 10-year period, they're pretty often, but how often, it's a rare occurrence. So it still has that feel of a Poisson. So I don't think that should surprise you that we're using a Poisson to study this type of process. So I guess the best way for me to show it, I try to write this out. Start at a time period and label it t equals 0. So starting at t equals 0 to some finishing point t, you're going to count the number of events that occurred in that interval. So then for some final number t, just imagine again, n of t is just the number of events. It's a random variable. So it's the number of events counting how many of those happened in the interval 0 to t. So n of t is just a function that's counting how many of those events occurred in 0 to t. So n of t would just be the number of car accidents in the interval 0 to t, or n of t is the number of hockey goals in the interval 0 to t, where t again is some, whatever it's going to be to you. Or n of t is the number of customers arriving at a post office in the interval 0 to t. N of t is a discrete random variable because you're counting how many of these occurrences can occur in an interval. And the support values could be, nobody comes, one person, two persons, three persons, up to infinity. So there's three properties of n of t that make it a Poisson process. You're a Poisson process if you follow these three principles. Stationarity, that just means if you look at every set of intervals that are the same length, like accidents per week, 0 to 7 days, the next 7 to 14 days, the next 14 to 21 days, the probability of so many events occurring in this interval is the same as the number of events occurring in this. It doesn't change from interval to interval. So the probability of n events in any interval of the same length should have the same probability. Independent increments. So the number of events in this interval does not affect the number of events in this interval does not affect the number of events. So it's not like just because you had more accidents in the first 7 days that it affects the next number of accidents in the next 7 days. And orderliness, that just means that it's almost impossible, and I know what does impossible mean, but it's almost impossible for 2 or more events to occur in a very, very, very small interval. So again, here we're looking 0 to 7 days. Let's break it down to 0 to 1 minute. You know, it's almost impossible. Like, think of the whole city of Indianapolis, that you have 2 cars exactly have an accident within 1 minute when you're looking at this on an interval of 0 to 7 days. So I mean, it's like even hockey goals. That's, you know, it's just saying back to back or almost simultaneously is very rare in this kind of process. So we call this a Poisson process. It's a random variable. And so n of t is just counting the number of successes in the interval of length 0 to t, where n is just what's the probability there's, you know, n events. And so you should notice exactly this is just a Poisson with lambda t being the rate or the number and lambda t up there. So if you expect a lambda of them to occur in let's say t equals 1 hour, if I was looking at 2 hours, then I'm going to have 2 lambda, and 2 lambda is going to go up there. So again, to me, it's just, I'm thinking of it as a Poisson random variable, and sometimes I don't even stop to think, oh, I'm doing a Poisson process. So I have 2 examples and the rest are others. So suppose on a summer evening, shooting stars are observed at a rate of 1 every 12 minutes. So again, you're thinking, you know, you can break up your interval, you know, every 12 minutes you see some. What's the probability that 3 shooting stars are observed in 30 minutes? So I usually see 1 every 12 minutes. So that means every 30 minutes I should see 30 12s shooting stars. So, and the question is, what's the probability of seeing exactly 3 shooting stars over a 30-minute time period? If I see 1 every 12 minutes, I should see, right, I mean, this is 2 times is 24 minutes, so I should see not quite 2, I mean 2 but not 3, so on average I should see 30 12s per every 30 minutes. So I'm going to let n of t be the number of shooting stars I see in an interval of length t, and that interval is actually in this case 30 minutes. Let 1 minute be the unit of time length. Then n of t is a Poisson process with lambda 112. Yeah, I guess I should have been more careful. 1 minute's the time unit, so again, you can see the difference. This is my t then, because I'm looking at 30 minutes, and then my lambda is 112 per minute. But I guess you can see over here, I'm in that Poisson random variable mode where I'm just trying to figure out what lambda is. So the probability n in a 30-minute time interval that you see 3, I'm just putting 3 in here for x, and I get a probability. So let me go down to, I have one more example. Japan earthquakes occur at a Poisson rate of 3 per week. Wow, that sounds really high. What's the probability that the next earthquake occurs before 2 weeks? Wow, so if the next one occurs after 2 weeks, that must mean there's 0 in a if I got to think about this right, in a 2-week period, I'm seeing 0 then. I hope that makes sense to you, right? What's the probability that the next earthquake occurs after 2 weeks? That means I see none in a 2-week period. So n of t is going to be the number of earthquakes in interval length t. Let 1 week be the unit length of time. So 2 weeks, that's where I'm getting, so lambda is 3. I expect 3 per week, but I'm looking at a 2-week period. So I should see 6 in a 2-week time period. But what's the probability? If I don't see the next one for after 2 weeks, that must mean I see 0 in that first 2-week period. So I hope the 6 is making sense. I see 3 earthquakes per 1 week, which would mean I would see 6 of them per 2 weeks. And what's the probability in this 2-week time period? I see none, and I'm just putting this into a Poisson. random variable. And down here, I actually explain why we use a Poisson random variable to simulate or for a Poisson process. And I don't know. I've talked about this in class, and I can't say that anyone's ever understood, and I don't know if it's the best explanation, but I'm trying to show how if we have random events occurring and break them up over the time, you can see that, again, imagine the way I did this is a Poisson process. Every once in a while, you're getting an A here, and you're getting, well, I don't know if you'll understand what I was trying to do there. And at the very end, I just have some more practice problems, and I have a whole Maple worksheet of practice problems that I think it's attached to the lecture, but if not, it's in there's a Maple worksheet that has binomial and Poisson. And if you want a video, that's also in YouTube now too. So the next thing you'll see is 5.3, and we'll talk again